Okay, good morning. Thanks for being here once again. Today we have a new seminar with our own Guilherme Raposo. He's going to speak about his ongoing project, what he's going to do, what he was doing, and what he's going to do now here in Aveiro. So please, let's hear about compact objects and elastic compact objects in general. Thank you.
Thank you, Lorenzo. So, well, hello everyone. I know that most of you know me. I'm from the group, so this is a bit strange in comparison with other seminars. But I was talking to Lorenzo and I figured out that I had several different lines of work that are not very explored in the group. And so it would be nice to sort of share with you what I've been doing, let's say, for the past year in collaboration mostly with some people from the mathematical department of the Institute of Superior Techniques, so Artur and José Natário. And I will basically apply what I did with them to new things that I want to explore here in Aveiro. And so what I'm going to talk about is elastic compact objects, in particular relativistic elasticity. And I want to start by stressing out, just a second, okay. So I want to start by stressing out why it's important to consider relativistic elasticity. And in particular, in the context of compact objects, there are several motivations for relativistic elasticity from a theoretical point of view, but I'm going to focus now on the motivation in the context of compact objects. So we know that astrophysical objects are typically modeled as perfect fluids, but we know that in reality, there is a lot of types of matter that are not fluids, like everything in this room. For example, in astrophysical context, the crust of a neutron star is a solid-like structure, that's why it's called a crust. And even if you go at higher densities, well, although this part here of the neutron star, this layer, is mostly considered a fluid, if you go even to more densities, you go to the inner core, and there is a big uncertainty what is the type of matter that is there, and not only the type, but also what is the state of that matter. Understanding if what is the phase of the matter here, if it's a solid, if it's a liquid, is very complicated when you go to these very high densities that you don't have big techniques to compute. And so this is the motivation to consider at least elasticity and why basically to explore what the solid-like effects can give in the macroscopic structure of these objects and how we can distinguish them, for example, from a simple fluid star. But there is a second motivation, which is related with exotic compact objects and tests of the black hole paradigm. I think most of you here work in things related with that, and we have heard a lot of talks on this. So exotic compact objects is anything that is not a neutron star or a black hole for the purpose of this talk here. And well, what we understand by tests of the black hole paradigm is understanding if the objects that we're observing in our astrophysical observations, such as those with the Event Horizon Telescope, the gravitational wave detectors, are really black holes as we understand them in general relativity, or are some other object that can have some, for example, some surface or a boson star, or etc. And something that is very related with that is what we call the Book-Dahl limit. So this is a result in general relativity that says that the compactness of an object must be smaller than 4/9 under some assumptions. And these assumptions mainly are general relativity and that the matter is described by a fluid. And what people have figured out is that if you sort of remove the assumption of isotropy, you can basically reach this compactness of the black hole using some other material models. And several works have studied this, what they call anisotropic fluids. But these are very, I mean, there's no big physical motivation for these anisotropic fluids. They just plug an equation of state for the anisotropic pressure with no big physical motivation. But what I'm going to motivate later in this talk is that elastic matter naturally describes anisotropies, and there is a very straightforward way from basically an equation of state of an elastic matter to obtain these anisotropic pressures. Okay, so without further ado, let's start by describing compact object in general relativity. I'm going to start with the most simple case for the presentation, which is a spherical symmetric object. Let's take a static spacetime also. So we know that the line element is this one here. We have heard about this also last week in the talk of Violeta, right? And then the stress energy tensor here is described by this diagonal tensor. But here we have tangential pressure in these last two components instead of just an isotropic pressure in the three of them. So if you plug these in Einstein's equations, what you get is the so-called Pullman-Oppenheimer-Volkow equations, these three equations here. But these are anisotropic actually because they are this extra term that appears in this last equation. For the anisotropic case, this is the only thing that is not that changing. This does not appear. So every talk that talks about this is always the same part, right? We always say, okay, this system of equations is not closed, right? Because we have more variables than equations. So what you need to close is specifying the equation of state. So basically, at some point, you need to talk about what is the macrophysics that's going on in this matter, right? And this, for perfect fluids, typically what we do is just put one equation of state for the isotropic pressure. Last week was exactly that case. We have heard a lot about this from Violeta. So we have, for example, polytropic equations of state. We have those more realistic equations of state motivated by nuclear matter models. For these anisotropic fluids that I discussed before from the other authors there, basically is what I said. You plug basically for the radial pressure some of these equations of state, and then for the tangential pressure, you sort of invent an equation of state by hand. And for the elastic matter, well, it's not intuitive, so we need to sort of review the theory of relativistic elasticity. And this is the part that I start by apologizing because this is where I'm going to get into a bit more detail and about a bit more mathematics.
Yeah.
Yes.
Ask a question.
Yeah. Please interrupt me at any point.
To be elastic, it has to be still diagonal, the stress energy, or is an extra assumption, or it's always diagonal.
Yeah, I don't think it has to be diagonal. So when I derive the theory of relativistic elasticity in the next slide, I'll show you how to get this stress energy tensor. At least the case that I've explored is always, well, it's not necessarily always an diagonal. For example, you can have terms here that are flux of energy momentum, but that's only dependent on the, well, the time dependence there, right? But I think you can have more general.
So but this still capture, I think, your like it's still quite general to have it diagonal, but with different components.
Yeah, that's quite general. So I'm going to show you exactly how to get to this stress energy tensor next. But again, this is the part that I'm going to say that is a bit more technical. So I try to do it in a very sort of schematic way to, well, to avoid boring you all here. So relativistic elasticity is actually quite an old formulation. It has been first derived in the 70s, I think, by Quintana. And then there is some more modern formulations from the 90s, and then this from 2000s, and actually. And well, the idea that we always start is basically by setting two spacetimes. So we have a physical spacetime. Imagine the spacetime where your object is, so your star, your physical star there. This star is deformed in some way, and then you want to consider the spacetime where basically is a snapshot of your star when there is no deformations. Because since you are in an elastic material, you want to compare basic stretches between things, right? You are deforming with respect to something. So that's why you have two geometries. Here I'm focusing on a concrete example, right? Spherical symmetric static spacetimes. So these are the two spacetimes that I said. And the first thing that you do is basically assign a mapping between these two spacetimes and the configuration gradient. So if you, well, are not very familiar with mathematical relativity and differential geometry, well, when you put coordinates, basically what you're doing is just relating these coordinates here, and the configuration gradient is just the derivatives of these coordinates on this manifold B with respect to the manifold, let's say M.
Yes, you work on space time, so the time in GTT is the same.
Sorry?
I equals space, what we call space time, GTT is the same, it's only.
No, sorry, this is a special metric, so there's no GTT there, yes.
It's space.
Yeah, this is a three-dimensional metric. Yes, so, okay, once you have this mapping, what you can do is compute the push-forward metric AJB. And so in an intuitive way, the push-forward metric is something that sort of projects your physical metric here, this G mu nu, into the, basically, this manifold that we have here, the material manifold. So what does this do? It's basically by pushing this metric to the manifold B, what you get is basically two different metrics. So this gamma and this AGB that are in the same manifold and allows you to define sort of an elastic strain. So basically the difference between the two metrics, the metric of your physical object in your reference frame, will allow you to define this stress. And everything in relativistic elasticity will be given by this AGB basically. And you can compute it easily by contracting this metric here with this configuration gradient. Okay, so this is a bit technical, so let me move more to the dynamics part. So I'm going to follow actually the formulation by Bike and Schmidt, which derives this by a variational principle of this action that we have here. And so with this action, you know how to obtain the stress energy tensor, basically just by taking this derivative here. And you know also that you can write the stress energy tensor in this form that we have here. So the technical part obviously is computing this quantity here. But this is actually easy if you consider homogeneous and isotropic materials. And what do I mean by homogeneous and isotropic materials? Is something, for example, that the energy density only depends on this sort of the strain of the material by these principal invariants. And principal invariants are just some combination of the eigenvectors of this matrix. So again, let me recall that we have the components of the matrix. You can compute the eigenvalues, the eigenvectors, everything. So everything can be straightforward. And so if you assume this material, you can sort of do quite a bit of algebra, but you can move from this expression here to basically compute this, what is called Cauchy stress tensor, which has this expression here in the end, where these E's that are here in the last part are basically the eigenvalues of this matrix H, that is basically the orthogonal metric. And whoops, I'm going in the wrong direction. And then we have this term here. And this can be identified with the principal pressures in the E direction. And so we arrive to the first result, even if you did not get the end. Basically, for homogeneous and isotropic materials, using this formulation of relativistic elasticity, we already get an expression that allows us to relate the pressure, the principal pressures, with the energy density, so through these derivatives. Again, these Ni here are basically the eigenvalues of that matrix H that I showed you before. And the thing that I noticed actually when I was preparing this presentation is that you can compare this with the first law of thermodynamics for perfect fluids, which relates sort of the pressure with the energy density of the material. You see clearly that there is a connection between these two. I mean, every expression is very similar, and these are related with the densities also. So there should be some connection there, although I did not have time to think too much about it. But at least it's interesting. But again, although we have this expression here, this is not enough to close the system of equations, right? We are just rewriting the pressures in terms of these Ni's that we have here. So to close it, we need to go one step further. So we compute these principal linear densities, these Ni, which are basically the eigenvalues of that matrix. And you get these eigenvalues that we have here. So M1 is, for example, this in terms of the derivative of this radial coordinate with respect to the radial coordinate in our original physical metric. And this is just this one here. So as you can see, we have here an implicit differential equation between N1 and N2, and N3 is the same in spherical symmetry. So this final equation is what will allow us to close the system and be able to compute everything and build stars with these materials. So just to summarize, because this is what I want. So you start with the TOV equations, right? This is not closed. You want to get an equation of state. In relativistic elasticity, if you consider isotropic homogeneous materials, you can write rho in terms of basically two parameters in spherical symmetry. Here, I'm replacing the Ni by these two variables. That is just a way to rewrite them. It's the same, just because this delta will eventually become the particle number density. And you know that how to compute the pressures through these formulations. So the pressures are these ones here. The system is closed by an additional equation that you get from this formula. So now basically you are able to solve TOB equations and build stellar configurations. And this is what I'm going to show now in this practical part of the talk.
Just to see if I understood. So your claim is that your calculation shows that you can start from an isotropic fluid, but seeing it in an elastic way and therefore produce anisotropies.
Sorry, can you repeat?
Because your claim is that your elastic fluid can reproduce some anisotropy physically.
So first, let me just maybe explain better. I'm not elastic fluid is not something.
Whatever you're doing in here now.
Yes.
Okay. As the assumption of isotropy.
Okay. Wait. Yeah, that's I should have not said it because this is a very weird thing because isotropy has a lot of different meanings in elasticity. So
That's
there
what
are.
I wanted to see.
Yeah, no, this isotropy has nothing to do with the anisotropies in the pressures, right? This is just isotropy in the material. So basically, what this means is that let me go above. So okay, this row here will depend on this N1, N2, N3, right? But by isotropy, I mean that permutations of N1, N2, and 3 do not change the energy density. Basically.
Okay.
So it only depends, for example, in the combination, rho depends on N1 times N2 times N3, because if you swap two of them is the same, or N1 plus N2 plus N3, and things like that. So people call isotropy a lot of different things. It's not my fault, sorry. But was I clear with that answer there?
Yes.
So I mean, it's just basically the material in terms of the macroscopic structure of the star is not the same.
It's not the property.
Yeah.
Because I was like, you want to write one isotropies, but you're assuming isotropies of where it comes from.
Yeah,
it's
no,
not that as well.
Imagine that you take a piece of the material, the piece of the material is sort of isotropic in that sense, but then when you look at the star as a whole, you don't really care about isotropy there. Actually, it's an isotropic as you've shown. So now I'm going to go to the main part of the talk, which is the applications of this formalism, right? And this first, so I call it second part here of the elastic stars was based on a paper that I put out a year ago with our collaborators. And here I want to, well, first do a simple case of an elastic star, right? And as in the fluid case, the most studied equation of state for fluids is arguably the polytropic equation of state, which has this form that you see here, right? This is a form that you probably all know. The pressure is a function of the power of the baryonic density, this probably here. This n is the polytropic index, and this kappa that I have here in the calligraphic is just the polytropic factor. And so if you want to write this in this elastic notation that I described before, it takes quite a bit of a different form, but it will look like this. And you can sort of connect this delta with the baryonic density, and you can sort of connect this kappa, not calligraphic, which is actually the bulk modulus of the material, with the polytropic index kappa that we have here. So you can sort of relate. But this is a way to write it in terms of this delta and n. So if you want to do a simple elastic generalization, the first thing that you can do is just put in, for example, here a quadratic term. So this is the piece that is the perfect fruit, and then you just add, let's say, quadratic correction or something like that in terms of this delta and n. There are some other properties that I did not say. For example, when delta and eta are 1, this must vanish. So that's why it has this specific form here. But you don't need to worry too much about that. This is just the simplest term that you can do. And this mu here is the shear modulus of the material. This is another elastic parameter that appears in the theory of elasticity. Okay. So now we have this equation of state, but we can ask why. Well, basically, the reference rate does not appear when we study, for example, fluids or polytropes. This is a parenthesis that I'm doing here. And so one thing to see is that, for example, if you compress your reference rate by a factor f, consider new reference state that is compressed by a volume factor. These delta and eta parameters are changed in this form here. And so you move from this, well, equation of state to this one here. But now what you can see is that you can incorporate this factor F in some definitions of new parameters in such a way that the energy density, so your equation of state, takes exactly the same form as this one here above, but just with some new parameters. You can sort of do a mapping between these parameters and this one in such a way that this looks exactly like this. So what does it mean is that basically choosing the reference frame is akin like what gauge choice. It really does not matter which reference that you choose because there is this invariance property when you scale the quantities. And one way to see that now is, for example, computing some quantities that are invariant under this normalization, and you are able to check that the baryonic density, the polytropic factor are invariant under this normalization, but also some new quantities that are computed. I'm not showing you here the expressions, but this dimensionless shear parameter and what I call an isotropic density, because I don't have any better word for that. And in such a way that when you plug these new quantities in the equation of state, it looks like this. So you basically see that any rho naught that we have here disappears, and you have, well, something that looks much more similar to the original fluid equation of state. Indeed, this piece here is the same as you expect. So reference frame dependent quantities really do not appear in the end. This does not happen for all materials. It's a particular case of some materials, as we'll see here. But this has, well, there's a lot of interesting properties. One of them is that you don't need to take one extra parameter when you are considering the, well, the model. As you see here, this is what I was saying. So basically, there is one parameter that you need to care about, which is epsilon, which quantifies the elasticity. So when epsilon is 0, you are in the fluid. When epsilon is different from 0, you have some elastic material. Of course, there is kappa here, the polytropic kappa, but if you know about polytropics, it's basically that's a scale. So you scale the mass, you scale the radius by this by power of this factor kappa. So you really don't care about, does not change the qualitative features of the problem. And then, of course, for each family of, for each epsilon, there is a family of solutions depending on the central density. So I think, yep. Do you have a question?
No, I was looking at the kappa of the enters once with k, the other with k to the n, and even with the different powers, it still scales in the equation.
Where, sorry? Ah, here.
Yeah.
No, but remember that this was a way to make this epsilon dimensionless. So basically what you care about is this term here, right? So you can encompass this in a new constant epsilon, so the elastic constant. Okay, so as I was saying, you have one family of solutions depending on the central density. So you take a central density, you get a mass and a radius for your star. You change it, you get another mass and radius, and so you can build what is this mass radius diagrams. I think you're all familiar with this concept. I think most of you work on boson stars and rocket stars, and I think you build a lot of solutions like this. So now let's look at the properties and what happens. So when we introduce this elasticity, so ignore the right panel for now, just focus on the left. So one thing that we see is that the elasticity increases the maximum mass of the star. So basically the fluid is the black line here, and as we increase elasticity, the maximum mass is increasing, so the stars become more massive. And as we increase also this elastic parameter, the compactness, which is basically the slope of this curve. So you see here in the orange line, we have the compactness of the photon sphere, the compactness corresponding to an object in the Bookman limit, the black limit here. The stars become more compact as the elasticity increases. And indeed, they start to go beyond the Bookman limit and even approach the black limit in some cases. Now, there's a dashed line here. This dashed line represents, there are solid lines and the part of the curve is a dashed line. This dashed line represents unphysical configurations. So that's now what I'm going to enter. I'm going to talk about the viability of the solutions and the physical conditions for them. I'm okay in time? Okay. So let's talk about viability. We want our stars to exist, so we want to have solutions like I showed you before, they are there. But now are these solutions okay from a physical point of view? So to understand that, we need to first check if the energy conditions are fine. And these are the weak energy conditions, strong energy conditions, null energy conditions, but also the dominant energy conditions. And also you want the causality to be satisfied, so everything, the sound speeds in the material should be below the speed of light, to have no problems in causality. In general, for an elastic material, there are 9 independent sound speeds. They reduce to 5 when, actually I'm missing one here, sorry. And they reduce to 5 in spherical symmetry. There should be another transverse wave in the tangential direction here. But okay, it does not matter. And so what I'm showing in the previous plot is that when the line becomes dashed, happens when the sound speed goes above 1. So this is what I'm going to show sort of here in the top panel. I don't know if you can see, but for example, this is one of the solutions in the border between the solid lines and the dashed lines. And what you see here is that this sound speed, which is basically the sound speed of a longitudinal wave that propagates in the tangential direction. So for example, if you are here on Earth, it would be like a longitudinal wave that propagates, for example, in the direction from south to north or from west to west or something like that. And it's vibrating in the same direction. And this is interesting because when people study anisotropic fluids, typically they only look at these longitudinal waves in the radial direction. So for example, a wave that is propagating from the center of the Earth to us, vibrating in that direction. So this extra velocity that will break the causality first is typically ignored in those studies. And so here with this formulation of relativistic elasticity, you are able to track all these velocities and check if everything is fine. Regarding the energy conditions, well, the pressures and densities are positive, so we don't really need to worry about the weaker, stronger than null. The only thing that we really care about is the dominant energy condition. And one thing that we have checked in this case is that the causality is basically a necessary and sufficient condition to verify the dominant energy condition. I don't know if it was a coincidence or not, but at least in this case it was. So everything here satisfies the dominant energy condition if it satisfies causality. Okay, another question is regarding stability. Here we have only looked at radial stability. There are other types of stability that you can study, but here we focus on the radial. The idea is always the same. You do this sort of linear radial stability approach where you do some small perturbation with some independent frequency here. And this is basically the radial displacement of your star. And this is another quantity that is rated with the radial pressure. And you basically get an eigenvalue problem for this frequency. And when you get a mode that is on the square smaller than 0, you have an unstable mode. And when it's on the square larger than 0, you get a stable configuration. And what we found out is that this is exactly the same as the perfect fluid case, in the sense that the radial stability happens exactly at the point of maximum mass. So, I mean, I don't think this is one, I don't think it was intuitive because in principle there's no reason to be so, but it happens that is the case. So it seems like that this maximum mass being a threshold for the radial stability is really some general property that we can, I guess, understand from other mechanisms. But one thing that I want to point out here is that we have some configurations. So this green line here is the photosphere that are stable and go beyond the photosphere. So, for example, the red line, I don't know if you can see the red line that is here in this inset plot. And also it is physically viable, this one, as I will show later. So as a final remark from just this part, what we have seen here is that although elasticity increases the maximum mass and compactness, objects that go beyond the Bookdown are unstable because they are after the maximum mass, and they also are typically in physical superluminal sound speeds. So they are not viable models for compact objects. But on the other hand, we have, for example, here some cases where objects can go beyond the focal sphere, so they have a light field outside, and everything is fine. So they satisfy the energy conditions that are below the maximum mass, so on the right of the maximum mass in this diagram. And so this could be a good candidate for ultra compact objects, at least from the point of view of if you want to study the properties of the light ring or the stable light ring within the object. That is something that I'm working on using these types of materials. I know that people here in the group worked on this recently, right? I think Eugene, Pedro, Carlos worked on the stability of the stable light ring for the case of, I think, broker stars, if I'm not mistaken. Was it the case? Yes. And so this is another candidate to do the same study because it will be interesting to understand if the results were very model dependent or are just a feature of the fact that there is a stable light ring there. Another thing that I want to mention here is that, for example, since the maximum mass increases, you can do a simple calculation and check that for a fluid, let's say you can have an neutron star with about 2 solar masses. If you, by these results, since the maximum mass can increase more or less up to 22% without violating the stability and the physical and breaking physical conditions, for an neutron elasticity, you can go up to 2.5 solar masses, which makes well, more compatible with the event GW19 or H14, where we had sort of this very heavy neutron star for our knowledge of neutron stars. Another thing that I want to point out is that let's look at this solution here. If you compute the shear modulus for this material with this E that we have here, so 10 to the -1, yes, we get a value for the shear modulus that is actually very compatible with the shear modulus that have been computed for the crust of the neutron star. If you plug like those values, typical density in the crust of a neutron star and the polytropic index that I use here. So actually let me go to the beginning very quickly because I have actually the plot there. Yeah, I don't know if you see here, this is basically a plot of the shear modulus of the neutron star, and you see here that this 10 to the 26 that I've shown you before is actually in the range of what has been computed here in this plot. So let me scroll back to here. And so I will conclude this first part of polytropic elastic stars with this motivation. And so now I'm going to move to a second part, which is a bit unrelated. But here I want to address the question. So we have seen that we have objects that create the photons here, but at the same time, these objects become very physical very quickly. So what about the question, what is the maximum compactness that we can get for a physical reasonable object? This is what I'm going to address in the second part. So again, this is related with sort of this problem of the Bookdown, right? So if you take, for example, the TOV equations with an incompressible fluid equation of state, so constant density, this can be solved analytically, and you get this compactness that we have here, this expression, and in the limit where the central pressure diverges, so goes to infinity, you get this Bookdown bound before 9. It's a nice calculation to do. So this is the Bookdown limit, and actually this is based on some assumptions, like I said before, and this is typically used as a roadmap for different types of exotic compact objects. So each of the assumptions to break to get some exotic compact objects, etc. But again, this was an incompressible equation of state, so the sound speed there is infinite, so it's not physical again. So a more interesting question is how compact can a non-exotic and casual object B. And so the causality condition is this one that we have here. So dp0 must be smaller than 1 and not actually larger than 0 for the sound speed to be well defined. And this is saturated by what's called a linear equation of state. So pressure is basically this sound speed squared times rho plus a constant. And for this equation of state, there is no analytical solution. So we need to solve the QV equation that we had before and get some bounds. And you get actually this bound here, this causal Buchdahl bound, which is around 0.364, which decreases to 0.354 if you assume rate of stability. So if you stop at the maximum mass. This one is a bit larger if you go beyond the maximum mass. So basically what this says is that there is no star made of a fluid that can be more compact than this limit here, this 0.354. If it's more compact, it will have some velocity that are above the sound speed of light. So now we want to generalize this to elastic materials because this calculation assumes an isotropic perfect fluid. And this is a bit more tricky because, well, for elastic materials, first, as I've said, we have 9 different sound speeds. Which of them we are fixing constant is a question because you cannot fix them all. But one thing that we know is that at the center, longitudinal waves must propagate faster than transverse waves. This is a condition for the physical stability of the material. I'm not going to go into details, but it is related to the fact that the isotropic sound speed must be larger than 0. That must be well defined, sorry, the square must be larger than 0. So the best choice that we have to make the most rigid object possible in elastic theory is by assuming that the longitudinal waves are constant, and in particular, we're going to put this constant to be the speed of light. So this will give the most compact elastic material. So the calculation is a bit complicated, so you need to sort of solve this differential equation here to build the equation of state. But this is the result. So in terms of this N1, N2, and N3 that we have from the previous formalism of relativistic elasticity, it will look like this, where this gamma is just basically the diabatic index, which is where the sound speed velocity here. Is epsilon and theta are 2 elastic parameters. So in comparison with what we had before, there is an additional elastic parameter that appears, which is a bit unfortunate. A thing that I also want to note is that in this case, you really need to care about the reference frame. You cannot get rid of this or not here, even by redefinition of the quantities. It will always be there. It will be an extra parameter that we have. Short of can see already because in this equation of state there's also this Roman text that is here, also in the fluid case. So we have 4 equation of state parameters, a dimensional flow, which is this or not, but you sort of can ignore it by absorbing in the scale of the problem and in the units. And also because it's dimensional flow, it will not affect the compactness when you calculate this dimensional quantities. And then we have these 3-dimensional parameters that will really characterize your solution, and you need to pick each of them. In most of the cases, I'm going to fix the sound speed to 1 because I want the upper limit that saturates causality. So basically, we'll have two constants that we need to change. And what actually we have seen is that our equation of state, this one here, this very complicated equation of state, encompasses several equations of state that have been studied in the literature. So the principles are phase material, which is the case where we go to the fluid limit, and then some other equations of state that have been studied in elasticity. So it's a more general equation of state that encompasses several others depending on the choice of parameters. And so this first part is the only part where I will allow the sound speed to be larger than 1, just to make a small remark. So if you look at how the maximum compactness grows with the sound speed, and you'll see something very interesting. So as the sound speed increases, of course, the maximum compactness will also increase. And as the sound speed tends to infinity, in the fluid limits on the left of this spot here, we are approaching the Buchdahl limit as expected. So this 0.44 or 49, if you want to be precise. But as soon as you turn on elasticity, so this new sheet slightly to the right, the Buchdahl limit goes sharply to the black hole limit. So Bookdal is really something very characteristic of the fluids. As soon as you have even a slight elasticity, this limit does not exist, you can go up to the black hole limit. So there's really sharp increase. But again, this Bookdal bound and this black hole limit that I'm discussing here happens for a physical configuration. This is for sound speeds that are becoming larger than 1. So again, we want to focus on the causal Bookdal bound. So I'm going to set now CL equal 1. Let me skip this slide for now, actually, and move to the calculating physical admissible solutions. So again, similar to the slide that I had before, now I want to have solutions that satisfy design conditions and also have subluminal sound speeds. So again, we have two parameters, this epsilon and theta that I showed you before. This makes the parameter spaces very large. So the analysis here is a bit complicated and requires a lot of exploration of this parameter space. But you sort of figure out that the maximum compactness saturates to this bound here, 0.469 that we have here. Actually, you can look here to different cases, and this bound that we have here is represented by this green line, which is a bit weird. Unlike the other lines, they don't behave as you expect. So it is this nice curve from the mass with these diagrams, but instead it just decreases like this. This happens because the parameters for this green line are a bit outside of the range for the normal elastic parameters in the reference state. But since the reference state is not an observable, we allow us to explore also this region of the parameter space. You can see that most of this configuration is invisible because it has this dashed line almost everywhere, but there is a region where it's physical, it is, well, above Bookdal actually. If you ignore this line, actually you figure out that the maximum compactness that you can have actually is very similar to the Bookdal limit. I don't know if it is a coincidence or not, but if you restrict, okay, if you remove this line here, the maximum compactness sort of converges to the Bookdal, which is interesting, but I don't have any explanation. It seems to be just a coincidence. Okay, but now let's ask about stability also, at least radial stability. You see here in most of these cases that are showing that compactness are beyond, so are on the left of the maximum mass, so they are unstable. If you admit physical stability and radial stability of the solutions, so saying that the density difference is more than the density of the maximum mass, the bound actually is much stricter. So we can look at this just piece of the parameter space. So we have here epsilon plus theta, and here we have theta. And the maximum compactness is around this area here. So around 0.1 in epsilon plus theta, around 0.3 on theta. And it gives this bound here 0.389, which is significantly larger than, for example, the fluids here. So we have here for the solutions that are, well, technically, physically okay from the radial stability point of view and from the energy conditions. They can have photon lightning outside and also the stable ring inside that we have checked numerically that is there. And just to show you that even in the exotic case, everything is fine. So I'm showing you here dashed the solutions that were satisfying the first bound, so only physical admissibility, so don't care about radial stability. And you see here on the top that basically the sound speeds are always below 1 in that case, and that the energy conditions are satisfied. So basically, if the blue line is above the respective green and red, the energy conditions are fine. So this leads me to the conclusion. So I think I showed you in the part 1 how we can get a relativistic formula that is suitable to compute stars. As I've shown you, I've computed these models of these compact objects. This can be interesting from the point of view of providing better models, for example, for neutron stars, but also to explore other compact objects and exotic compact objects in particular. So these elastic stars actually were very interesting to construct. This was just a very simple case where the entire star was made of a polytropic elastic fluid. but it had some nice properties, mainly the increase of the mass and the increase of the compactness. And it was interesting to also to note that the shear modulus that we obtained for this solution is actually very compatible with the shear modulus of the crust of a neutron star. So it's not a very idealistic shear modulus that we got. And in the third part of this talk, I showed you our results on generalized compactness bounds in general activity. And these compactness bounds basically can be summarized in this table here. So the book down limit that we obtain for a fluid moves from the 4 nines to 1/2. Physical visible solutions, so again, solutions that are causal and satisfy the energy conditions. The bound moves from 0.365 to up to 0.469, so much more compact. While if you impose radial stability, this bound gets much stricter, but it's still larger than the fluid case, and you can go up to 0.39 more or less. So, regarding ongoing work, I did not have time to basically go into much detail, but currently I'm working on multi-layer neutron stars, in the sense that obviously a neutron star is not made of elastic material from the, let's say, the core to the crust. There is a region that is fluid. So I want to better describe neutron stars by providing, for example, pieces. This piece is elastic, this piece is a fluid, this piece is elastic again, for example. And you see how it will basically affect the structure of neutron star if it's very distinguishable from, let's say, just a fluid neutron star. And also on extending the formulas that I showed you before to beyond spherical symmetry. The formalism still applies beyond spherical symmetry, is just much more complicated than what I showed you before, because computing the eigenvalues of that matrix when you are not in spherical symmetry is just a mess. Even mathematically does not like it. And to conclude, I'm also working currently in basically just a 1+1 numerical evolution of these stars that I computed. We are just setting the formalism to, well, to make it appropriate to evolve in numerical activity equations. And eventually we would like to, well, to reach a point where you can study the stability of the inner light ring and all those issues regarding the stability of compact objects. So that's it for me. Thank you.
Many thanks, Guilherme. You got perfect time.
Oh, you're welcome.
Guys, please, questions, thoughts, comments?
Yeah, sure.
So about the elastic stars, you have a parameter which is the small n.
The small n? Yeah, the polytropic index.
Yeah, consider 1/2 and 1 of the same.
Mhm.
So is there any reason to consider other values or some real number, dependent number? And if you do so, does that change much the maximal mass that you can acquire?
So let me go wrong side. So the answer is well, the answer is no. So basically, don't forget that we have this this calligraphic kappa, which is a scale. So basically, the mass is separated by this kappa. So you can always change kappa in order to get any mass that you want. Typically, the n changes the profile of these curves. So again, this is a polytropic index. There are some, I don't remember exactly the bound, but there are some n's from which above this n you don't have stars. So it's not, you cannot, the pressure does not vanish at the radius. And these ones are the ones that are typically used for model neutron stars. So you can construct this sort of piecewise polytopes, so junctions of different polytopes that are good to model, let's say, the realistic equations of state of neutron stars.
More questions? More questions on Zoom?
I have a couple. You don't want to go? Me, definitely question. So you are addressing the stability of these guys.
Radial stability.
True. I know that you see it clearly, but since you have some kind of anisotropies, some kind of tangential pressure, do you expect the picture really holds when you are
letting the perturbation being also angular pattern.
Yeah, actually, I think something that would be very interesting to study would be maybe, well, the first simple thing that would be interesting to study would be axial perturbation, because that's the first intuitive thing that you can go. Yeah, because of course there is this field is not spherical symmetric. I mean, it's spherical symmetric, but the potential pressure is different. So something different is happening in that direction. And I think when you go to those perturbations, it would be much more.
Do you think an axial and polar would be actually decoupled?
Actually, I don't know. I think they will be decoupled. Well, at least in this background, depends if you go to a more general background, in that case, perhaps it's not decoupled, right? So, I mean, if you put this perturbation in the spherical symmetric background,
And the last thing was about your last point, like tidal deformations. Yeah, like ongoing work.
yeah.
And just curiosity, some of the ambiguities of neutron stars were partially addressed by universal relations
Mhm.
that you can find in your I love Q relation rules. So the question would be here, you still have ambiguities in the values that you can give to your elastic parameters. Do you think there is a kind of universal counterpart that can help you addressing your open problems with this theory, with these objects that can accumulate?
I mean, at this stage, I don't think, I mean, maybe eventually there will be a counterpart for that. But at this stage, I'm simply, since I don't have yet the formalism to go beyond spherical symmetry, and so studying the law of numbers is not something that is very intuitive there. I'm not sure exactly how far away can I go with it. So I'm still exploring really how to extend the formalism in that case. Although I'm more focused now on the two other parts of the multilayer neutron stars and the numerical relativity exploration of parameter space. But yeah, I expect that there will be some kind of inverse relation that will also happen in this case. I don't see why not, especially because these in principle are more compact than the other neutron stars, and the universal relation lies in some way related with going towards the black hole limit and the properties that black hole have. They should be there.
Regarding the multilayer,
Mhm.
do you have any intuition regarding
Yep.
layers? Because you said you can also put like elastic to elastic.
Yeah, so let me see where I am. So if you remember the beginning of my presentation, I had this slide with the sort of layers of the neutron star, right? So so this will be sort of a spoiler perhaps to next presentation or something like this. But one thing that I've studied already is consider everything a fluid and then put just the solid first. And in this case, you set sort of the parameters in order to have basically this distance of this first around 1 kilometer, depending where you put the threshold of the density, basically. And in this case, there is no big change in the profile of neutron star. So because, of course, you can see this is a very small region of the neutron star. It's a region with a very smaller density, at least with respect to this. So there's not much mass there, so it's expected to be not very different. But on the other end, if you consider a solid core, well, things can be quite different there. So if you do the reverse. But again, to answer your question, it basically depends where you set the transition region, right? The interface region. And you can sort of choose that in order to match this distance.
Last question. Well, if not, let's give Guilherme. So I think that's all for today. There should be only in December one face-to-face seminar on the 12th. It should be a Monday by a Brazilian researcher that is in Lisbon and will come here. Despite this day, the rest are all non-presential. So thank you guys.
Thank you very much.
Bye-bye.
Bye-bye. Bye everyone on Zoom.